Okay, so today's video is going to be about quantum mechanics, and we will focus on the concept energy, time, uncertainty principle. Okay, so the first of all, we all know about position. Wait, that's a very bad color to choose on this. We all know shit. No, delta x delta p is greater than h over 2. We all know about this, right? That change in position times change in momentum equal h bar over 2, and delta x, which is change in position, is loose notation and sloppy language for the standard deviation of the results of repeated measurements on identically prepared systems. This equation over here is often paired with one more equation, which is our topic here. It is change in time and change in energy is less equal, more than, not less, more than h bar over 2. Okay, here we have energy and time. Here, one more thing you might have noticed, position, which is x and t, they go well with each other. In the position, sorry, not here, I'll write this down, I'll write it up. They go well with position, time, then position, time, four vector, okay, which is ct. And then when we talk about P and E, we know that P and E, P, P and T, which is which equal, if I write equation, P is equal to E over C, and this is the energy momentum 4 vector, energy momentum 4 vector. Okay, but you might have noticed this all is about relativistic huh, relativistic relativistic how do you spell vistic relativistic equation. These are relativistic quantum mechanics, QM. But we are not doing relativistic, as Schrödinger equation is non-relativistic. Equation is non-relativistic, is non-relativistic, as the other two, which is Dirac and Klein-Gordon equation are relativistic. 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 As Klein-Gordon equation is written as this plus this is Klein-Gordon equation. Okay, and Schrödinger is the combination of sorry, not Schrödinger. Dirac equation is the combination of this and uh, this. So here what we will be talking about is how to derive energy time uncertainty principle, the equation. Okay, for this, after all, in position, momentum and energy are all dynamical variables, measurable characteristics of the system. We can measure them at any given time, but time itself is not a dynamical variable, changing variable. Not at any rate. In a non-relativistic theory, you don't go out and measure time of a particle as you might its position or its energy. We cannot measure its time on like other quantities. Time is the independent variable of which the dynamical quantities are functions. Okay, so if time is the main, the functions like position and energy and momentum are times in dynamical quantities. Dynamical quantity function. Quantities or quantity function. Quantities. Okay, this is a independent function. Independent. It doesn't depend on anything. Independent. On this, everything depends on independent variable. Well, it's a very interesting concept, right? Time doesn't depend on anything, but other things depend on time. If you want to measure position, you need time, energy, you need time, and then for momentum itself, also we need time. It's my like, okay. Then, in particular, change in time in the energy time uncertainty principle is not the standard deviation of the collection of time measurements. Roughly speaking, I will okay. It is the time it takes the system to change substantially. I'm very horrible with English. As a measure of how fast the system is changing, let us compute the time derivation of the expectation of the values. Let's suppose this is a certain we're taking x, p, and t. Q is this value, these factors. So derive. We will use derive. We will using k as derivation. So we know that d partial, not partial d over dt, which is time dependent derivation of q is d over dt of q, not q, psi, and q of psi. Okay, and then this further goes into, if I multiply this derivation into these, I'll get psi of d of dt and q of dt. This is first, plus then d of, sorry, not d of dt, psi of psi comma d of dt of q psi, plus, I hope you can see this, psi of d over dt of q. No, not this. Now we'll be doing. You might have understand what I'm trying to do here, right? I multiply this time dependent variable with each one of these to get this whole part. Then we know that Schrödinger equation says I h bar, what am I doing? I h bar of partial d of or d wave function of dt equal Hamiltonian energy operator, where this is equals to p square over 2m plus v. So we can write d over dt of q as 1 minus 1 over I h bar Hamiltonian h q, not h q, h wave function. Did I put lines here? Oh, I didn't put, I put comma, not lines. I'm wrong, sorry. Here, this should be the correct one, yes. And q, sorry, q of lambda plus 1 over I h bar. Now we have lambda. Okay, now we're doing the same thing but with the Hamiltonian thing. First we did with this one, now we are doing with Hamiltonian plus again over here 1 over I of h bar q this q psi of h. Okay, I was wrong about this one. This is only d over dt of q. That's it. But here h bar is Hermitian or of course Hamiltonian as well. So sorry, h bar hq of, was it hq or different? No, it was different. Of this is, this line should be there. This equal psi of sorry, h q this. What do we have here? Is this and this as this. Okay. Then this becomes d over dt and q is I of h bar h of this plus d of dt q of course. I noticed something that here these two variables over here and this. So what happened actually is that this whole thing turned into h and this whole thing turned into q, to write in a simple form. And so in final we got this equation, and this can further be simplified to write, this is an interesting and useful result in its own right. In the typical case where the operator does not depend explicitly on time, it tells that the rate of change of expectation value, the value we expect, is determined by the commutator. Commutators are these. These are what the commutators are. Not this. And of the operator with the Hamiltonian, in particular, if q commutates with h, then q is a constant. So we are taking q as a, if it commutates, constant. If it commutates h. And in this sense, Q is a conserved quantity. It's a saved quantity. So in simple, we can write it as H. This is a symbol of this Q is greater than H bar of 2, and this is D, this one over here, Q of dt. It's saved this, and then this, let's define energy, which is this. So yeah, if dH is equals to energy operator and T operator change in T is this over this operator over this operator, what do we get? We get energy T and energy time and energy and time more than H over 2. So it does, yeah, it is correct. Yes, yes, yes. Okay, let's do a overview. And that's the energy of time uncertainty principle, but notice what is meant by time, change in time. Here Q is actually d of this change over dt. This symbol is actually times d. This is how it actually is. So t represents the amount of time it takes the expectation value q to change by one standard deviation. In particular, standard deviation is mostly the distance between two certain values. If this is a value, let's suppose 1 and this is 2, this gap here is standard deviation and so on. And so in particular, change in time depends entirely on what observable q you care to look at. Observable, the change might be rapid for one observable and slow for another, but if the change in energy is small, then the rate of change of all observables must be very gradual, or to put it in the other way, if any observable changes rapidly, the uncertainty in the energy must be great. So that means if there is a change in observables rapidly, there must be a very huge change in energy operator. Large. It is that rule. So yeah, that's it.